Okay, so let me start. Okay, so what we are doing harmonic functions. Okay, we are doing harmonic functions. You know what is the meaning of that? The definition, quickly recall. Let omega be an open set in Rn. We say u is in C2 omega is a harmonic function. Harmonic function if Laplacian u at the point x is equal to 0 for every x belongs to omega. Okay, then we are doing the very important theorem, the properties of harmonic function, which is known as mean value property. Can you recall what is that property? Mean value property. Can you recall what is that mean value property? Let u is in C2 omega be harmonic, then for any x belongs to omega and for any r positive such that for all those r, for any r, for any x and r positive such that bxr, of course, since omega is an open set, so we can always find some r. We have this property. This is a very important property. 1 by the volume of the ball bxr integral over bxr of the integral uy dy is equal to 1 by the surface measure of the ball del bxr integral over the surface of the ball, that is the uy dy is equal to at the point ux. It is sometimes resembles the Cauchy integral formula in complex analysis. Not exactly, it is something like that. Okay, so this is so any for a harmonic function, the u at the point x can be represented as this from this integral form. Okay, 1 by the volume of the ball bxr is equal to this. So what we started the proof, but we could not able to complete the proof, right? We have proved that, if you remember well, we have proved that we first define r such that 1 by sigma del bxr integral over del bxr uy d sigma y. We define this. And what is the domain of the r? What is the domain of phi? Can anyone tell me? Can you tell me what is the domain of the r? What is the domain of the r? What is the domain of phi? What is the domain of phi? What is the domain of phi? This r varies from where? Where to where? What happened? Manish, Vivekanand, Devranjan, what is the domain of this phi? From where this r varies? Manish? Open 0 to infinity. Not, no. For all those r such that Bxr should contain in omega, otherwise this does not make sense. I told you in the beginning, for all those are such that Bxr is contained in omega. Anyway, if you don't want to learn any, what I can do. Anyway, so this is the phi r. Okay. So ui d sigma y, and we proved that. If you remember, we proved that. We proved that limit s tending to 0, us is equal to ux. Whatever you know, you just see the steps and then, okay. Anyway, so this we have proved. So, and we know that us equal to phi r, phi of r. We have proved this. Anyway, now we have to prove. So this is done. So this is done. 1 by del bxr del bxr uy dy is equal to ux. That is done in the previous class. Now we have to prove this one. Okay. So what we have proven, that sigma del bxr, the surface measure, integral over the surface of the ball, uy d sigma y, we have proven that it is equal to ux for all those r positive such that bxr. But still we have to show that, this is equal to, we have to show that 1 by bounded, the measure of the whole ball, bxr uy dy. I hope you understand the difference between this integral and this integral. Okay, and we have to show this. So this is done. Now we have to show this. Okay. Now you just consider bxr uy dy. Okay. Now use the, so bxr is this is x, this is your r, and this is bxr, right? This is your ball. Okay. Now you have to use the polar coordinates. I have taught you in the polar coordinates. Okay. So what will be the polar coordinates? Can you tell me what I can write? Integration bxr uy dy. What I can write? Can you please tell me? Can you please tell me what I can write in polar coordinates? Integration bxr integral u over bxr. Please, can you tell me? Okay. You can write. You can check. Just check that. What I can write? 0 to infinity. Sorry, 0 to r. Let's say. Okay. Del b xs uy d sigma d sigma ds. Okay, so this we can write. This is equal to, and you know that, you just see del bxr d sigma y is equal to this. So I can use in this integral this we know already, right? This is equal to 0 to r. This is equal to ux into sigma del bxr. Okay, this equal to this, I have used this fact that integral over del bxr uy d sigma y is equal to ux into sigma of del bxr. Okay. Now what we have, that is equal to 0 to r ux sigma of del bxs ds. Yes, this is sigma ds. Okay, that is, this is it does not depend on r, so it comes out from the integral. So this is 0 to r sigma del bxs ds. Can you tell me what I can write this is equal to? Can you tell me what I can write this is equal to? Can you tell me what I can write this is equal to? Yes, can you tell me what I can write this is equal to? 0 to r, the surface measure of the ball of radius s, which I integrate from 0 to r. What should be this? Just think about it. This is a surface measure. This is the s, and I am varying s from 0 to r. So what I will get? What I will get? Can you tell me? Anyway, that I will get the measure of the ball of radius r. So these imply that, so this is the bxr uy dy. This is 1 by p of xr bxr uy dy is equal to u of x. Okay, so this completes the proof. So this completes the, this proves that 1 by the measure bxr, the mean value property. Okay, this is very important. This is 1 by sigma del b xr del b xr uy d sigma y is equal to ux. So this is the mean value property. Okay, mean value property. Okay, anyway, so next is the, so if u is a harmonic function, then it will satisfy the mean value property. Now I will prove the this is a theorem. This is a very important theorem. Is that if and only, let's say u is in C2 of omega and satisfies the mean value property, can you say that f is a u is a harmonic function? Okay, let u is a C2 omega and satisfies that for all bxr which is contained in omega, there holds this ux is equal to 1 by sigma del b xr del b xr uy d sigma y. So it is what is this, what it's given, that given is that u is a C2 function and satisfies every b xr in omega, there holds this. So the mean value property, so this property satisfies. Okay, this property is already there. Okay, so this is equal to this, ux is equal to the integral over the surface of the ball uy d sigma 1 by sigma of del b, the measure of the ball, or measure of the surface of the ball. Okay, so this is given that ux is equal to this. Then my claim is that then u is harmonic. Then I am claiming that u is harmonic. Okay, so the proof goes like this. The proof goes like this. Let phi r, the same quantity we defined, right? 1 by sigma del b xr del b xr uy d sigma, the same quantity. Okay, then just using the previous calculation, or if you see, if you wish to see the previous, I have computed it by the previous computation calculations. We have phi prime of r is equal to 1 by sigma del b xr. Okay, if you just derivative this phi r, we have already done in the proof of the in the last theorem. This will be del b xr Laplacian uy into dy. Please check if you want to check. Please check. I request you to check. Okay, check. is nothing to check because I have already done this proof. Okay, phi prime of r is equal to this in the previous computation. Okay. So phi prime of r 1 by the surface measure of del bxr integral over del bxr Laplacian uy dy. Okay. Now what I have now we know that now from the hypothesis what is given from the hypothesis that phi r is given to be is equal to u of x for all r. Can you tell me why? Why? Can you tell me why? Anyone can you tell me why? Why? Why phi r equal to ux?
Those are given sir, that VXR is always contained in sigma.
Because it is given that ux is equal to this and this is our phi r. This is our phi r. Okay, it is equal to ux for all r for all such r such that bxr is contained in omega. Anyway, okay. So for all r such that bxr is contained in omega. So what can I say about phi prime of r? Huh? What can I say about phi prime of r? What can I say about phi prime of r from this equation? Just from the above, what can I say? For every r, phi r is equal to ux. So what is the derivative of phi prime of r?
U prime x into del x over del r.
It's equal to 0. It's a constant. It does not ux does not depend on a r. So whatever r you take such that bxr is contained in omega, phi r is ux. So phi prime of r should be equal to 0. Is that clear? Is that clear? Yes or no? Phi prime of r equal to 0. So what does it imply? So what is your phi prime of r? Phi prime of r is this. So this imply that integral bx of r Laplacian uy dy is equal to 0 for all bxr which is contained in omega. Okay. This imply 1 by the measure the same thing bx of r Laplacian u of y dy is equal to, I have nothing, I have just multiply by this, I just multiply the above equation by 1 by measure of bxr. That's it. Okay, so that should also be 0. Now you consider this difference. Now consider the following difference. Okay, 1 by measure of bxr integral bxr Laplacian of uy integral dy minus Laplacian of ux. You just consider the modulus of this difference, okay, which I can write as 1 by measure of bxr integral of bxr. I can put inside the integral minus u of x dy. Why I can put inside the integral? Can you tell me why I can write this? Because if you see that if I integrate Laplacian of, because u does Laplacian of ux, it does not depends on y. So if I integrate the Laplacian of ux comes out, it will be measure of bxr. So measure of bxr and 1 by bxr cancels out. So you will left with Laplacian ux. Okay. So I am writing Laplacian of ux as equal to 1 by bxr integral Laplacian of ux dy. This I can write. So this is less 0. Then where this will go? The above expression will hold this. this expression will go to where? Can you tell me? Letting r tending to 0, where this above expression will go? Can you tell me? Where it will go?
What 0?
Yes. Why? Because I have considered u is a C2 function. So Laplacian of u is, and you can just take u to be Laplacian of ux equal to vx. This is a continuous function. So now use the, I have already said that for a continuous function, Lebesgue differentiation theorem. For a continuous function, this is a straightforward proof. 1 by measure of bxr integral of fy dy bxr will converges to f of x as r tending to 0. Okay, this will converges to f of x if f is a continuous function. So apply this here. So instead your f is now, so you can, this is your fy, this is your f of x. So this comes. Okay, that is this means 1 by bxr integral over bxr fy minus of f of x, this will converges to 0 as r tending to 0. Okay, so you use this fact. Okay, use this fact, it goes to 0. So what we obtain? If it goes to 0, we obtain that this imply what this imply Laplacian of ux is equal to limit r tending to 0 1 by measure of bxr. This is a straightforward bxr Laplacian of uy dy, and we know that this is equal to 0 because phi prime of r equal to 0. Okay, this is your phi prime of, we already have seen. So these imply Laplacian of u at the point x equal to 0 for x to be in omega. Since x is arbitrary, this proves that Laplacian of u at x equal to 0 for all x in omega, and this proves u is a harmonic function. Is that clear? Harmonic function. Okay, so if u is a C2 and harmonic, this is if and only if it satisfies mean value property. So if and only if. So if u is harmonic, then it satisfies the mean value property. If u is a C2 function and satisfies the mean value property, then u has to be harmonic. Is that clear? Okay. Next very important theorem, it's something called regularization. That means, so now, so what if you see in the previous all those theorems, just remark, this is crucially used, right? That u is a C2 function, sorry, u is a C2 in omega and u is harmonic or something, right? U is harmonic or it satisfies the mean value property, right? Satisfy mean value property. In both the theorem, if you find, you will see that u is equal to u belongs to C2 function is crucially used, as you see that as u is C2, I can do this Laplacian of u, as I said that I can use there in the inequality that Laplacian of u minus Laplacian of ux minus Laplacian of uy 1 by the measure goes to 0 as r tending to 0. So it's this fact is crucially used that u is a C2 function. Okay. Now the next theorem says that we don't actually require u to be C2ness. Just a continuity will enough. Okay. So the theorem is a very important theorem. So we somehow want to take a less regular function, not a C2 function. Just a continuous function will work for us. Okay. Let's see how. Let u belongs to continuous with omega and satisfy satisfies the mean value property. That u of x is equal to same thing, that del b xr. For all pxr which is contained in omega. Okay. Just you look at this. U is a continuous function, not given to be C2 function, and it satisfies the mean value property. Then U is in fact C infinity of omega. How important you see. Just a mean value property. You cannot conclude from our previous theorem that U is harmonic. No, because U is not given to be C2. It is not given. U C2 is not given. U is given to be a continuous function and satisfies this mean value property. If a function satisfies the mean value property, then U is C infinity, and hence this implies U is harmonic. Because for harmonicness, we at least need U to be C2. Otherwise, how can I define the xi square? How can I define this del 2u by del xi square if U is just only continuous given? But this theorem proves that if U is a C continuous function and satisfies the mean value property, then U is a C infinity, okay, smooth function, and hence U is harmonic. Of course, then you can C infinity functions means U is in particular U is a C2 function. You apply the previous theorem and you say that U is a harmonic function. But this is very important. The first step is that if U is given to be a continuous function and satisfy the mean value property, then U is a C infinity function. Okay? Is the statement clear? Is the statement clear? Is the statement clear? Is the statement clear? Hello, is the statement clear?
Yes, sir.
Okay. So any idea how to start the proof? We have to prove something C infinity. So what I should do? Okay. So you remember what we did, a mollification. You remember? And convolution. You remember? I said now if f is just a L1 function, if you convolve with a mollifier phi epsilon, then this is a C infinity. You remember this? That it's a very bad function. If you convolve with a smooth function, then the convolution operator makes the whole f convolution f will become C infinity, right? We have to use this type of idea. Okay. Okay. Let phi epsilon is the standard mollifier. You know what is the mollifier? So px is nothing but e to the power minus 1 by 1 minus mod x square. If mod x is less than equal to 1, 0. If mod x is greater than 1. We have done this. Epsilon means ux by epsilon. Okay. This will be the standard mollifier. This is called standard mollifier. Okay. Now let x belongs to omega epsilon. You remember what is omega epsilon? I have defined this omega epsilon as set of all x in omega such that distance between x to del omega is greater than epsilon. That means this is your, let's say, omega. You take this is, let's say, epsilon. This is omega epsilon. You make your domain little bit less than the omega epsilon. There should be an epsilon distance from the boundary. Okay, this is your omega epsilon. Okay, as we know how to define a mollifier in a bounded set. Now U convolution phi epsilon x. This is nothing but, you know, bx epsilon uy 1 by epsilon to the power n phi of x minus y by epsilon dy. Okay, so this is equal to 1 by epsilon to the power n bx epsilon uy phi of x minus y by epsilon dy. Okay, okay. Again, we write this in a polar coordinates. This part, we'll see how. This is equal to 1 by epsilon to the power n. You know how to write down 0 to epsilon del bx r. R varies from 0 to epsilon. Okay. uy phi of x minus y by epsilon d sigma y dr. I can write this. This is equal to this. Just I have used the polar coordinates, nothing more than that. Okay, is that clear? Now you just think phi of x is this. That means it depends only on the mod x function. So if I write down phi of mod x is equal to phi of x, is that clear? Phi of mod x is equal to phi of x. If I just you do the mod x, then again I will get same thing, phi of x. So what does it mean? Phi of mod x equal to phi of x. What does it mean? Can you tell me? What does it mean? So you just think your x is this. This is your origin. Your x is this. This is your mod x. So the function phi, the value of the function phi over mod x, all those points on the circle, if r equal to mod x, all those r equal to on this circle r equal to mod x, phi x equal to phi of does not change sign, does not change the value. So the function phi depends only on the radius. You understand what I mean? That means phi is a radial function. Phi is a radial function. It only depends on mod x, not on x. So if you take this point and you take this point, the functional value of the phi is same, because phi of x equal to phi of mod x, right? Because this point the value of mod x and this point the value of mod x are equal, right? Am I able to? Is it clear to all of you? If you see, this is some x1, this is an x2, but mod of x1 is equal to mod of x2. If mod of x1 equal to mod of x2, then phi of mod of x1 is equal to phi of mod of x2, because it only phi depends only on the mod x. That means the distance from the origin. That means the if you draw a circle around radius mod x, then the value of the function phi is same along that circle. That means phi is a radial function. Is that clear? Is that clear?
Yes.
Okay. So this is the thing. So that means this phi x minus y minus epsilon. So this is actually phi of mod of x minus y by epsilon. Right? So it depends. So distance from x to y. That means this is your x and y is varying here. Y is varying here. So whatever you y take, whatever y you choose, the value of phi is same along this circle of radius del b x of radius r center x. That clear? So I can write this is as, this is the only trick and only understanding, only this is the unique concept I will be using in the proof, that phi is a radial function, so it can come out of the integral. Okay, because over the integral phi is a constant, because phi is only depend on the radius r, not on x or y, right? Epsilon phi of, so x minus y by epsilon, so this it depends on x minus y. What is the distance of x minus y? If y is in the surface of the ball, x minus y is r, so phi of r by epsilon comes out. So this is del b x r uy d sigma y dr. Okay, this integral. Okay. So this is equal to 1 by epsilon to the power n 0 to epsilon phi of r by epsilon del b xr uy d sigma y into dr. So this I have come down. So what I can write this equal to? Can anyone tell me what I can write this equal to? Because u satisfies the mean value property. Yes, that means this is equal to ux into del b xr. Right? So this is equal to 1 by epsilon n 0 to epsilon phi of r by epsilon into u of x, because it satisfies the mean value property, sigma del b xr. Okay, that means u comes out, ux comes out. You have 1 by epsilon to the power n 0 to epsilon phi of r by epsilon sigma del b xr dr. Okay, so what is this? Again I am using polar coordinates. That means this is equal to this, I can write as 1 by epsilon to the power n 0 to epsilon. This is I can write as del b xr. Again phi is, so phi of x minus y I cannot, because phi is a radial function, d sigma y dr. Right? This I can just, this I break it like this. Sigma of del bxr is nothing but integral del bxr, just this d sigma y. Okay, and why phi r goes inside? Because phi is a radial function. Right? Just use the Fubini's theorem here. Okay, this, and what is this? This is nothing but, this is equal to ux into integral bxr uy dy. Sorry, phi epsilon y dy, and we know that the modifier integral bxr phi epsilon y dy is equal to 1. So 1, and that is equal to u of x. So we have proved that. So these imply what I have proved: u convolution phi of epsilon at the point x is equal to u in omega epsilon. Now use the u of x. For each point x, u convolution of phi epsilon at the point x is actually equal to ux in omega epsilon. What I have proved. Now we know that we use the convolution theorem that if u is a continuous function and phi epsilon is the modifier, then u convolution phi epsilon is in fact a C infinity function. Also we did it in the tutorial class. So this is a left hand side is a C infinity function of omega epsilon. Right? So these imply ux belongs to C infinity function in omega epsilon. Okay. Now, but we have to show that this epsilon is arbitrary. Epsilon is arbitrary. And omega is an open set. So what does it imply? These imply u is in C infinity of omega. So for every epsilon, ux is epsilon is arbitrary. We can let epsilon tending to 0 and omega is an open set. So we have u belongs to C infinity. Clear? So what I have used, the only idea I have used here is the polar coordinates in the proof. That is why I have said no, polar coordinates is very important. First idea, and second idea is you have to convolve, because we know that if one function is very rough function, if you convolve with a modifier, it becomes a smooth function. So u convolution of phi epsilon at the point x is ux if u satisfies the mean value property. If you satisfy mean value property. Clear? If u satisfies the mean value property, then u convolution of phi epsilon is equal to u of x. Okay. Once I have this, then we know that u convolution phi epsilon is always a smooth function. That means right hand side is also a smooth one, because ux is equal to u convolution phi epsilon. So u is a smooth function, C infinity in omega epsilon. Since epsilon is arbitrary and omega is an open set, this implies U is C infinity of omega. Okay? Okay. So an immediate corollary says that if U is C omega and satisfies the mean value property, then U is harmonic. Why? The proof is simple. Since U is C omega and mean value imply U is C infinity. U is C infinity omega. So in particular, U is C2 omega because C infinity omega, so C2 omega. U is C2 omega, then you use the second theorem, imply U is C2 omega and satisfy the mean value property, imply U is harmonic. Okay? So with less regularity, we call that if U is only a continuous function and satisfies the mean value property, then U is in fact a harmonic function. Okay? Okay. And also this proves that all harmonic functions are C infinity because you will know. Okay. Now so what three theorems we have done. One is mainly the mean value property. For the harmonic function. Okay. If and only if we have proved, right, mean value property. And we have seen that if U is harmonic, then it satisfies the mean value property. And even if U satisfies the mean value property, then U is a Laplace. Just continuity plus mean value property imply U is a harmonic function. Okay, this resembles very similar kind of that if f is an analytic function, then it has a integral representation like with the help of Cauchy integral formula, which we used. Now this is the one of the most important theorem, and in fact this is the important theorem, is that let U be harmonic. This is a long theorem I will prove today in omega. Then U is real analytic. Of course, omega is a subset of R, open subset of R. Let U be harmonic in omega, then U is real analytic in omega. Is that clear? So we have to show that if U is, so we have just used that U is a C infinity function, and we know that if U is a harmonic function, then U is also a C infinity function. As you just the previous theorem states that if U is a harmonic function, then we have proved that if U is continuous, so if U is a harmonic function, it will satisfy the mean value property. So automatically, if we convolve with it, we know that if then U is a C infinity function. So now the question is, this is more serious. Not only C harmonic functions are C infinity, harmonic function is in fact a real analytic function. Any idea how to show that it's a real analytic? You remember there is an if and only if condition for real analytic function I have studied, right? We have done this proof. A function is U is said to a C infinity function U is real analytic if and only if it satisfies some property. You remember? Anyone remember? Anyone remember that property? Manish? Manish, are you there? Shivani? Govind? I have done something like if and only if u is a C infinity function, then u is real and if and only if satisfies something. You remember that property?
Yes, sir. For any compact set, there
Ha
is a
ha ha. Yes, yes, yes. Good. Let K is a subset of omega be a compact set. We want to show that there exists R positive, M positive such that d alpha u of x is less than M this will satisfied by u. Okay, if u is a harmonic function, C infinity, of course every harmonic function is a C infinity function, then we have to show that d alpha of u is less. Probably satisfied for every compact set K in omega. Okay, so step 1. Step 1. If x naught belongs to omega and bx naught comma r is contained in omega, then we will show that d alpha of u at x is less than a constant ck r to the power n plus k norm of u L1 of bxr. We will show that, of course. Step 1. If x naught is in omega and bx naught r is contained in omega, then I will show that d alpha of ux is less than this. Okay, when mod alpha, when this mod alpha is equal to k, then we can compute explicitly what is ck. Okay, then ck is 2 to the power n plus 1 n k to the power k by alpha n. What is alpha n? Alpha n is the measure of the ball 0 1. Okay, and c0 is for k equal to, these all are ck equal to 1 2 dot dot dot, and c0 is 1 by alpha n. Okay, because k starts from 1, so there is also a c0, which is, we will show that if x naught is in omega and bx naught is contained in omega, then d alpha of ux is less than this. The derivative of the multi-derivative modulus of d alpha of ux is less than ck by r to the power n plus n norm of u of L1 of pxr. Okay, let us first try to prove this step 1. Okay, proof of step 1. So our aim is to prove this d alpha of less than m. We want to show first step we will prove this, and then we will see how we can prove from this step to this one. Okay. Okay. So proof of step 1. Just a minute. One small remark before the proof. If u is harmonic function, then we know that this implies u is C infinity. These also imply del u by del xi is also harmonic. Is that clear? Why? If u is harmonic, then del u by del xi is also harmonic. Is that clear? Why? Because if you just check inflation by del xi, this will commute. Laplacian u of 0. Okay, just check this. Okay, if u is harmonic, then del u by del xi is also harmonic. Is that clear? You can check. It is just simple, right? Because u is a C infinity function, whatever derivative you take, so del you understand. I don't have to say all the derivative are commute. So you have to use del square by del x1 del x2, or like that is del square u by del x2 del x1. This type of property we have to use. Claret's theorem, what is called. Okay. So if u is harmonic, then its all derivative is also a harmonic function. The partial derivatives. Okay. This is a small, because this I will use this. Okay. So let's do the proof of step 1. First, let us consider the case alpha equal to k, I said. So let us consider the case. Let us consider the case mod alpha is equal to 0. Okay. So we have mod alpha equal to 0. That means ux. That means alpha equal to 0 means only the function ux. Okay. Okay. So u at x naught is, I can write by mean value property because u is an harmonic function. This I can write, right? Just use the mean value property. Modulus of u, I just take the ux naught is equal to this, I take the modulus. Okay. This is less than equal to 1 by Vx naught r, Vx naught r uy dy. Is that clear? I just take the modulus inside. This I can write, this measure I can write 1 by measure of B01 r to the power n. I can write this, yes or no? Because this is first step is 1 by, this is translation invariant 0r, right? Then because bx, and then I can write this step equal to 1 r to the power n. So this is bx naught r uy of dy. Okay, so what we obtain now? We obtain u of x naught is less than c naught time r to the power n integral bx naught r. This is nothing I have done. What is c naught? You just check c naught. What is c naught? C naught is this, right? Where c naught is 1 by measure B01, which is equal to 1 by alpha n. We say that alpha n equal to the measure of ball size, a fixed quantity depending on n. So C0 by r to the power n. Okay. This implies step 1, just you check step 1 holds. Step 1 is true. Step 1 is true for mod alpha equal to 0. Okay. Now I have to show that. Let's see what I should show. Now since u is harmonic, this implies del u by del xi is also harmonic. As I said in the remark, if u is harmonic, is derivative. So your del u by del xi, so Vx is now your del u by del xi, and we know that V is harmonic. So we know that if V is an harmonic function, then it will satisfy the mean value property. Then it will satisfies the mean value property, right? Because V is an harmonic function. So that is what is V? If your V is nothing but del u by del xi. So xi at the point x naught by mean value property 1 by, for any r I can write. So b x naught r by 2, because for r it is inside the omega, that means for r by 2 is also inside the omega. So b x naught r by 2 u of xi y dy. Clear? Is that clear? Now what I can do here, can anyone tell me?
Why we take, sir, r by 2?
What by r by 2 we take? Because we want to, just a minute. We want to have a iteration r to the power n plus k. This k I want to bring it up. Okay. You will see why. Because this r to the power n plus k I want to bring it up. Okay. Clear? You will see. Instead of 2 also you can, if we want to, you will see why. You will see. I will tell you why. You will see just now why. Okay. Because I want to integrate, I want to estimate bx x naught r. I will tell you. I will draw a picture. You will see. So I can write this. What I can use here? Can you tell me? Del u by del xi dot 1 ui into. So what I can use here? This I can write by integration by parts. By parts. Okay. 1 by b x naught r by 2. What I can write here for integration by parts? This is the 1. This is the 1. What I can throw the derivative at 1, 0. The boundary will come. So del b x naught r by 2 uy nu iy, the outward unit normal, into d sigma y, just using integration by parts. Okay. Now modulus of uxi x naught is nothing but less than equal to 1 by b x naught r by 2 del b x naught r by 2 modulus of uy. Nu y is the unit normal, that means 1, modulus is 1, uy d sigma y. Now you see why I have taken r by 2. R by 3 would have been better. R by 4, whatever you have to take, I will tell you why. You will see now. Okay. Now I can take the supremum out. So uxi at the point of x naught is less than equal to 1 by bx naught r by 2. This I take the supremum over u del b x naught r by 2, and the rest is the measure of del b x naught r by 2. Okay. So what I obtain? Just a minute. Uxi at the point of x naught is less than equal to 1 by measure of bx naught r by 2, right? Supremum of uy over the ball del b x naught, not the ball, the surface of the ball, and sigma of del b x naught r by 2. Now I can write this as this I can write as the surface measure of the ball of radius r by 2 at the center x naught. This is nothing but surface measure of the ball 0, 1 into r by 2 to the power n minus 1, because surface measure. And again we can write this as this is sigma del b 0, 1, okay, by measure of 0, 1 r by 2 to the power n into r by 2 to the power n minus 1 into supremum of uy del b x naught r by 2. Okay, clear? Okay, so we know that we denote sigma, the surface measure of ball is wn minus 1 by alpha n, r by k cancels out, I get r by 2 into supremum of uy del b x naught r by 2. Now I will draw a picture, then we understand why I have taken r by 2. So here is your x naught. Okay, so this is your, let's say, r by 2, and this is your another r by 2. That means this is your r, right? And this is your omega. This is your omega. Okay. Now what I have estimated, the derivative at the point, the partial derivative of u at the point x naught is less than some constant time supremum of uy on the surface of the ball r by 2, right? So this is again r by 2. So we have still a distance from the, because our main ball is bx naught r, right? So I have estimated using r by 2. So still I have a distance of r by 2 left, because your supremum of y varies in del b x naught r by 2. That means y is varying in this inner circle, inner ball, inner surface, right? So this is bigger ball is your b x naught r. we have another distance. So if I take another, so you take any y here on the surface. Okay. Now you draw a ball of, you draw a ball of radius r by 2 here. This is your radius r by 2. Then by of r by 2 is strictly contained in bx naught r. Is this correct? by r by 2 is contained in bx naught r, because this is your x naught, this is your y, this is x naught r is the bigger ball. So y is in the r by 2 surface. So if I draw a ball of radius r by 2 centered at y, so this at max this can touch the ball. So it is contained in this. Is that clear or not? So you can say instead of r by 2, I can take something less than r. Clear? Now r by 2, that 2 factor is not that important. Okay, I can take r by some c is greater than 1. Then we have to choose that c minus 1 by c is the distance. So you have to take the smaller ball which is strictly inside the bx naught r by 2. So we have some distance, so that after you reach at y, you can draw a ball of center y, and so that it is contained in r. Is that clear now? Is that clear? Whoever asked? Ankit, you have asked, right?
Yes, sir. Clear.
So that we are still inside the bx naught r by 2. Okay, this is the main funda. Okay. Okay, so what we have proved, u of xi at the point x naught is less than wn minus 1 by alpha n into r by 2 into supremum of uy over del b x naught r by 2. This is this is your equation 1. Okay, now fix del b x naught r by 2. Then clearly, as I draw the picture, y naught r by 2 is contained in bx naught r. Okay, and contained r. Now you apply step 1 with alpha equal to 0 on u1. Alpha equal to 0, we get u at y naught. Y naught is a fixed. Just step 1, c0 r with the radius r by 2 n. Right? I got this. Step 1 for alpha equal to 0, which we have already proven, which is now you see we have y. This is, so now by naught r by 2 is contained in bx naught r. So which is less than equal to, because mod y is a positive function, this is a bigger set. So c naught r by 2 whole to the power n integral b x naught r uy dy, because bx naught y naught r by 2 is a subset of bx naught r. So we have this. Okay. So this imply supremum. So this is independent. So this is independent of c. This depends on y naught, but this integral is independent of y naught. You understand? So I have made this integral inside bx naught r by 2. Now there is no dependence on y naught, right? Now I can write supremum of u y naught, modulus y naught is in del b x naught r by 2 is less than equal to c0 by r by 2 whole to the power n. See, because I take the supremum of y naught, right hand side does not depend on y naught now. That is why I have taken r naught by r by 2, so that I can have a space. Okay, now you will see u naught for all y naught. I estimated. Now I have uy supremum of del b over the del b x naught r by 2 uy. I have estimated. See, del b x naught r by 2 I have estimated. Now you substitute this supremum less than this here. here. Suprema means this part is less than equal to this part. Okay. So substituting back in 1, we get uxi x naught is less than wn minus 1 by alpha n r by 2 c naught r by 2 whole to the power n bx naught r uy dy. Okay, now you just can see what I am getting. This is your constant c1 and 2 goes above. Your constant is c1 by, and main important is r to the power n plus 1 I am getting. This exponent is important. R to the, because I have taken one derivative, so alpha is here, mod alpha is equal to 1. I have getting n plus 1. So when mod alpha will be k, I will be getting n plus k. That is important. Okay. Bx naught r uy dy. Clear? So I have proved the step 1 for alpha equal to 1. But now I have to prove that for any mod alpha equal to k. So I will use the induction. Okay. Now this is a big theorem, and this is not tough, but this is a big theorem. Okay. Now we need to prove for any k. Okay. So any k. Let mod alpha equal to k. Okay. Then I can write as d alpha of u is, I can write dou by dou xi d beta of u. Yes or no? Because one derivative will be beta, where mod beta is less than equal to k minus 1. Right? If mod alpha equal to k, d alpha u is du xi d beta. Okay? Okay. Since u is harmonic, I said that all its derivative will be harmonic. Since d alpha u is harmonic, I can write d alpha u at the point x naught is 1 by bx naught r by k. Again, you ask me why I have taken k. You know why I have taken k. Because I have to want some number which is greater than 1. Okay? Bx, because d alpha is harmonic, I can apply the mean value property on d alpha of u. Okay? D alpha u of y dy. This I can write in this way. This is not a difficult now. Because d alpha I have written like this, d beta of u. Okay. So now I can use here the integration by parts. Integration by parts. Okay. Integration by parts. So this is equal to 1 by bx naught r by k del bx naught r by k d beta uy mu iy d sigma y. Okay. This implies d alpha u at the point x naught. Now we know that our inequality holds for d beta, right? Because we know that I have induction step that it holds for d beta. This is less than wn minus 1 by alpha n r by k to the power n minus 1 by r by k to the power n to supreme. Same thing. You take the modulus of nu I is finite, 1. So mod of d beta comes out, then comes the measure of del b x naught r by k. I can write at del b x naught r by k as del b 0 1 r by k to the power n minus 1. The same step. Del b x naught r by k to d beta uy. Clear? So this is a trivial step. See this step. Here I have to use the induction step. Induction hypothesis that it holds for k minus 1. Okay. Hypothesis, induction hypothesis. Okay, because your beta mod beta is less than equal to k minus 1. So it holds for 1 to k. 1 is I have proven for 0, I have proven for 1, and I assume it holds for 1 to k minus 1. So I have to use the induction step here. Now, let's say this is equation number 2. Now applying induction step. We obtain that d beta uy is less than c k minus 1 by k minus 1 by k r n plus k minus 1, because k minus 1, right? And I got this is bx naught r uy dy. This is the from the given condition. This holds true. I get it from the induction step. Okay. Now you substitute this quantity, equation number 3, in equation number 2, that here, this part. Because I have assumed that induction step, so d beta of uy should satisfy this thing. Okay. I have substituting 3 into, we get d alpha u at x naught, n minus k is there, some constant ck by r to the power n plus k. So we have proved the steps. Okay, so this proves the step 1. Now it's easy. This proves the step 1. Okay. Proof of step 2. Proof of step 2. Choose R positive such that 0 less than R less than distance between some compact set. You have a compact set, right? Compact set. Distance between k to del omega. Okay. This implies for, because this is your omega, let's say. Your compact set is here. Okay. Distance between k omega, R should be less than this. This your R you have chosen. Distance is the least. Distance is the infimum of k. You know, distance between. So this, let's say this is R is less than. So this is less. R should be less than. So that I can, if I take a ball of radius, so such that this implies for all x belongs to k, Bxr is well inside omega, because I have chosen R to be less than k into omega. So for all x, so at max, this, if you say this you can take the radius r. R is less than distance between k and del omega. So we are quite inside the omega. That is the only reason I have chosen. Okay. Now from step 1, I get d alpha u at x is less than a ck r to the power n plus k bxr uy dy for all x in k and for all alpha. This is just a step 1. Okay. Now you define let your k tilde, I define a new set. K tilde is like this. X belongs to omega such that distance between x and k is less than r. So your k is this set. So what is the k tilde set? The distance between x and k. So all set inside is there, because distance, if x is inside k, what is the distance between x and k? 0. So 0 is less than 1. So all these points are there, also R. So this is little bit bigger than K. So this is your bigger set. So this is your K tilde. Okay, this is your K tilde set. Just a bigger set. Also less than equal to R. This is a closed and bounded set. So K tilde is compact. In Rn. Also BXR is contained in K tilde for all x in K. Because this is a R distance. Maximum distance is R. So if you take any ball of radius, this should be contained in K tilde, of course. Okay. Therefore, d alpha ux is less than so this is your bxr is now contained in K tilde, right? bxr is contained in K tilde. So less than equal to, if you just check the nk to the power k by alpha n r to the power n plus k. K tilde mod. I have not used, this is your ck, just the constant ck, and K tilde is nothing but, because this is contained in K tilde, mod u is a positive function, so integral will be greater than, less than K tilde mod of u. Okay. Now use the fact that k to the power k is less than k factorial into e to the power k. Yes, this is trivial. E to the power k is 1 plus dot 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 plus k to the power k by k factorial plus dot dot dot. These imply e to the power k is greater than k to the power k by k factorial, right? These imply k to the power k is less than k factorial into e to the power k. Trivial, right? So if you see that less than equal to m times k to the power k m times k to the power k into 2 to the power n plus 1 n by r whole to the power k. This I obtain. So what I have done, I have taken m to be nothing but just fixed k tilde is your fixed compact set mod of u. So this is some finite quantity. Depending on this m depends only on the compact set. If I integrate, so it depends on the compact set k. Okay. Okay. And now k to the power k is less than k factorial. So m into less than equal to k factorial into e to the power k. So I can push it inside e to the power n plus 1 n by r to the power k. Okay. And this imply m k is your mod alpha factorial r tilde by minus k. Okay. So this imply that d alpha u of x is less than m mod alpha factorial r to the power mod alpha. Okay, sorry, not this is mod, no, this is alpha factorial mod, sorry. Okay, mod alpha factorial e to the power. Clear? And this proves, so this is the thing, for every compact set k in omega we want to show that, and for all alpha we have to show that d alpha of ux is less than m times mod alpha to this. Clear? Okay. This is a very big theorem, and at least you should understand the case k equal to 1. Okay, then it is enough. If you understand k equal to 1, that is all right. Okay, if you don't understand the rest of the step, that's fine, but I have done it in a detailed way. Okay. Okay, so hence u is an analytic function. So if u is harmonic on omega, then u is an analytic function. Okay. Shivani, Govind and Ankit, anything else you want to ask me? That's all today. So what we have proved that? We have proved that. So we have done many things, right, today? Anyway. Okay. So what we have proven is that today's class we have seen that this this mean value property is an if and only if condition. If U is harmonic, then it satisfies the mean value property, and if U is if U satisfies the mean value property, then U is harmonic. Then we did it in a less regular setup. That if it's just a continuous function and satisfies the mean value theorem, then it is a C infinity function, and hence it's a harmonic function. And next and finally, what we did is that if U is a harmonic function, then U is a real analytic function in Rn. This is a very, very, very important property of a harmonic function. Okay, which previously we have just seen that if U is a harmonic function, then it will be a C infinity function. But now what we have proved that if it's not only a C infinity function, it's a real analytic function in Rn. And you will see what are the implications of this in the later class. Okay, since it's a real analytic function, we could have a many applications of harmonic functions. Okay, so next class we will do some applications of harmonic function. Okay, that real analytic functions. Okay. Thank you.
Thank you, sir.
Thank you.